We've been dealing purely with single-threaded Swift up until this point. Now the time has come to introduce the first concurrency management technology you'll use extensively when programming in Swift. Before we begin, let's quickly overview the available concurrency technologies inside the Cocoa ecosystem. First of all, we have the dispatch library, which will be the focus of this section. It's a relatively low-level library with a lot of features. However, it's very powerful and has a smooth learning curve. Next, we have its slightly bigger cousin, Operation and Operation Queue. It has many similarities with Dispatch, although it's a higher level abstraction that makes it more suitable for complex, multi-step task management. Next, Swift has had its own native concurrency system in consideration in Swift evolution for some time. However, it's still some way off release. It may become a feature of Swift 5, which is likely to be released in 2018. As such, we can't cover this now. Dispatch and operations are, however, powerful technologies that can be used in the meantime. Finally, we have Cocoa's older, traditional manual thread and lock style concurrency systems. We will not be covering these at all, and manual thread management should be considered these days as archaic. So let's get started with our first concurrency system, Grand Central Dispatch. Grand Central Dispatch, to give it its full name, is also known as GCD, and more often nowadays as just Dispatch. It's a queue-based concurrency management system that uses a pool of traditional threads under the hood. The last point is very important. Queues are a very different concept to normal operating system threads, and whilst all dispatch work is performed on a system thread, this is an implementation detail. The key concept is that you should declare queues that match your requirements and let the dispatch library handle the best way to perform this work under the current system conditions. In order to understand how dispatch works, let's first introduce its most fundamental concepts. There are additional features to dispatch that we won't cover in this session. Instead, we'll focus on the features that serve the majority of use cases. First off, we have queues. Queues are similar to threads, but should never be considered as the same thing. They are lightweight and allow us to describe our requirements whilst leaving the resource management details up to the system. Dispatch queues always operate in a first-in, first-out FIFO manner. Queues can be either serial or concurrent. You'll discover that dispatch queues are at their most powerful when working with serial queues. Queues also have a concept known as quality of service, which is a simple system that allows us to describe our use case requirements to the system, giving it useful extra information in the management of resources. Once we've created or accessed a queue, we create a dispatch work item representing a simple task to execute on a queue. Often this is just a closure, although it's also possible to create work items themselves for more control. In this session, we'll just be using closures, however. This is the most common use case since dispatch is at its most powerful when reserved for reasonably simple tasks. Finally, we're able to create dispatch groups that manage a group of tasks, linking, joining, or synchronizing them, and giving further control over concurrent execution. Let's start by explaining a few simple use cases for types of queues. The simplest use case for a dispatch queue is a concurrent queue. As we add work items to the queue, they are executed in parallel. It should be noted that the concurrent queue does not give us much control over the number of concurrent tasks. This is left up to the control of the system. When working with a concurrent queue, we'll often want to join or synchronize the completion of our work items. This is one of the roles fulfilled by DispatchGroup. We're able to use the group to be notified of the completion of all of our closures. Let's go straight to an example of processing in a concurrent queue. We're going to perform a set of concurrent tasks that load a number of text files from URLs and count the occurrences of words in those files. Then we'd like to aggregate the results perhaps. First of all, we declare our concurrent queue. These are the most important arguments. We must give our queue a label. In a larger application, we should name our queue more carefully, but we'll just use a simple label for this example. The second argument specifies the QoS, or quality of service of our queue. We have a number of options that can be browsed in the documentation. I've chosen User Initiated, describing a high priority task that was directly started by the user of our application. Finally, in the attributes we specify concurrent, since serial is the default. Our task processes an array of URLs, so let's imagine we have those already. Also, we need a collection in which to store our results. I haven't detailed this here, and we'll return to this shortly. Then we'll loop over our URLs and perform the task. We dispatch to the queue using the async method that has a single closure argument with no parameters. Inside the closure, we define our task. In this example, let's imagine we're loading the text files, then we'll count the occurrences of each word and save them to the results. Now returning to our results collection, what collection type would be suitable here? We have a problem. Our work closure will be executed on any number of dispatch pool threads. This means we need to use a writable, thread-safe collection to store the results. In fact, none of Swift's standard library collections provide this feature. Also, Dispatch provides no way to simply associate data with a queue task. This means that aggregating our results becomes non-trivial and demonstrates a good reason why concurrent queues are not often used for these kinds of data processing jobs. For a task like this, we need a higher level abstraction. In fact, this is exactly the kind of job to which operation and operation queue are much better suited. As mentioned before, DispatchGroup is the tool we use to synchronize the execution of multiple concurrent closures. Let's cover its API now. Let's jump straight into the code. We create the queue as before. I'm using a concurrent queue again, but we can also use a group with a serial queue. We simply create a DispatchGroup instance. Then when we enqueue our closures with the async method, we pass the group as the group parameter. Finally, we register completion closure with the group's notify method. We have to specify on which queue we'd like the closure executed. Here I'm just using the same queue again. This closure will be executed when all of the group's closures have finished. Notice that we need to register our completion closure after we have enqueued our tasks. Otherwise there'll be no tasks in the queue and the notify method will execute the completion immediately. And that's all there is to it. Okay, now let's do an example of working with a concurrent queue with quality of service and a dispatch group in a playground. So we're doing async work here, so we need to enable needs indefinite execution in the playground. And I have a function here, queueExample, which has a single quality of service parameter, which we're going to use to set the quality of service of the concurrent queue that I'm creating here. I'm also going to create a dispatch group so I can synchronize the completion of all of these closures. And in the method here, I just have an array of numbers from 0 to 10. For each number, I'm going to print a message in queue with the number that's being enqueued or about to be enqueued, and then we're going to execute async on the queue, passing in the group so we can do a notify at the end. And then we're going to print another message with the number to show when the closure is actually executed. I also have here a print statement enqueued, which we display when all of the closures have been enqueued. And finally, in the group notify, we print that we're done and also finish execution of the playground to tidy things up. So the first example, I'm going to use user initiated as the quality of service. And let's see what happens. Let's bring up the log here and run the playground. And you'll see that we more or less get an even mix of enqueue, execute, 2 enqueues here, 2 executes, but mostly enqueue, executes, all the way down to the bottom. And we see the enqueued print statement almost at the end before notify is called. So that shows that when we use user initiated quality of service, our jobs are executed almost immediately. Now let's change the quality of service to background and see how that affects the output. Now you'll see that we have a very different result. We have entries for enqueue for all of our blocks, and then we see the enqueued print statement, and then we see all of our closures executed, and you'll notice also here not quite in sequence. 1 and 0 are out of sequence, and also 7 and 8 are out of sequence. And we see the done message at the bottom here. So that shows that when we're using very low priority quality of service, the system doesn't try to execute our closures anywhere near as strictly as if we're using user initiated.